So we will continue our discussion uh, on electrodynamics. So let's look at this Maxwell's equation. How we saw how they can get modified in presence of a dielectric medium or a material medium. So these equations also look different when they enter into a conducting medium. So let's look at that. Uh, of course, now if I I mean to move to how the equations will be modified. So just let's look at how the equations would look like in free space. So this is, I'm always starting with these differential equations so that you are familiar with this Maxwell's equation. You should know it really well. So curl of E is minus del B by del T. Then curl of B is equal to mu naught A plus mu naught epsilon naught del E by del T. Okay, so this is how the Maxwell's equation, classical Maxwell's equation, look like in free space. Now, when we talk about a conductor, so a couple of things that conductors are special. Okay. So first of all, they so if you have any free, they have a lot of free electrons or free charges, and if you have an electric field, so you will get a current density which obeys your Ohm's law. Okay, so this is your in a conductor, the current density is given by sigma into E, where sigma is your conductivity. Okay, so this is, you know, from Ohm's law. Okay, so which you can write as V is equal to I into resistance. So here this conductivity is nothing but your reverse of 1 by rho. Here rho is the resistivity, not the current density, but this symbol again we are using similar symbols. So rho is here resistivity, which is different from your charge density that we are writing here. So this rho and this rho, they are different. So if we know this is like the current density is sigma into E, so and of course within a conductor, so we know there are no bound charges because it is not a dielectric, so you cannot have any polarization of a conductor. So there is no bound charges in a conductor, so polarization is 0. So the first equation will remain unchanged. So you can just simply write rho F by epsilon naught. The second equation, of course, also remains the same. The third one also remains unchanged. And the final one, so curl of B, so in place of J, we can write as sigma into E plus, since we are talking of a material medium, so instead of mu naught and epsilon naught, we will have the corresponding permeability and permittivity of that material into del E by del T. Okay, so this is how the equations will be modified in a conductor. Now let's explore a little bit about this AC conductivity, the conductivity itself, and how this conductivity is different when we apply a oscillating or this electromagnetic field. So when we talk of this electromagnetic field, that means the electric field is varying with respect to time. So it is an oscillating field. Similarly, magnetic field is also oscillating. So this is also an oscillating magnetic field. So both are they are oscillating, and this is what gives rise to the electromagnetic field. Now, what is the effect of that on the conductivity of the conductor? So let's look at that. So the conductivity also can be expressed in a fundamental way. It is related to it is related to this number of charges or electrons in the material, then the charge of the electron, and the average velocity of the electron in presence of electric field. So this expression comes from a model which is based on known as a kinetic theory. So it is like simply a kinetic theory of gases is applied to electrons. So in a metal or in a conductor, so we have lots of free electrons, and a model was developed. So this was developed by a Drude. Okay, so it was in beginning of last century, and so just using the kinetic theory of gases, which means in kinetic theory of gases, what you assume that there is no interaction between individual uh, gas molecules. Now they move all in random direction, okay, and also so the collision is either like so there is a mean free time or a mean free distance they travel before a collision occurs. Okay, so this normally you define by parameter, let's say lambda, mean free path, or a mean free time tau. So a particle or a gas molecule, or in this case a electron, so it will move some distance lambda, that is equal to the mean free path, and then it will collide. And once the collision happens, so it is as if it can move in any random direction. Okay, so once just after the collision. And now if you take the average velocity of such a collection of gas molecules, or in this case, let's say electrons. So if you take the average velocity, so it will be actually equal to 0. Why? Because we are saying they are all moving in random direction. So now you just add up all these velocities together and take the average, so it will be always 0. So that means in this case, J will be 0. But and this velocity, this average velocity, also sometimes known as a drift velocity. Okay, so in metals, so it is also known as drift velocity. Now, but then how do we get a current or a current density in a conductor? So for that, you have to apply a electric field. So if you apply an electric field, so then this average velocity or the drift velocity will be non-zero. Okay. So now how do we find out, can we find out an expression? So now if we, okay, we know, so n, so let's look at this expression for J. So in order to find this conductivity or the current density, we need to know what is the average velocity of this electron.
sugar sugar তাহলে পুরা হাই আছে
So
আমি তাহলে স্যার
what
পরে
is
বেশ
n?
ଦେଖିବା ହଉଥିବ ଏଟା କ୍ଲାସ ଦେଖିବା ମାନେ ରାଉ କେବେ ଗୋଟେ ହେଇଥିଲା କି ଆଜି ଆରମ୍ଭ
Can you request everyone to switch off their mute? Okay, thank you. So this n, what is n here? N is number of electrons per unit volume, and E is of course electron charge. Now, in order to find out this electron, sorry, the current density, so we need to know what is the average velocity is. So how do we calculate that? So everything what we are doing right now is more from a classical understanding, or taking a classical assumption. Everything is based on a classical understanding. Okay, so since we are talking about a collision, so during so the in the collision process, so the electron will exchange some. So if let's say electron is colliding with maybe some neutral atoms or particles, so it is colliding with that, and due to that the velocity changes. Okay, now during this collision process there will be definitely exchange of momentum. So how much momentum is exchanged? So this momentum exchange due to the collision, so this is the momentum exchange during collision is equal to MPV. Why? So why we are saying this is equal to ME into V? So ME of course is the mass. So just before the collision, okay, so it has certain so the average velocity is not zero, but just after the collision the momentum, sorry, the average velocity is zero. So this is one of the assumptions in this model. So since before the collision the average velocity or a velocity is v, and after collision this velocity is zero, so therefore the change or the momentum transfer during this collision process, so whatever maybe it is colliding with, so during this collision process the change in momentum is me into v. And we can, from this we can also calculate what is the force that is acting on the electron during this collision process. So this force acting on the electron, so this F is equal to, so this rate of change of momentum, which is simply as me into v. And another interesting term we are introducing here is tau. What is tau here? So tau is the time between two successive collisions. So that means the electron carries a momentum of MeV up to a certain time tau. Then once the collision happens, so it loses all its momentum, So there is an exchange of momentum. It loses all its momentum, and then again, so it starts moving in random direction, and until again it gains this average velocity, and then next collision happens, and so on. So this process becomes that goes on, and this force that acts for a duration, time duration tau. Okay, so this is also known as a, a yeah. So this is a collision force basically. Now, but what is uh, so this is the collision force, and if we use now Newton's second law, so we can write down this me. Now the rate of change of this, the Newton's second law tells us that me into dv by dt, that is the acceleration, is then equal to this f collision, which is given by minus me v by tau. Now, if I apply an electric field, so there will be a resultant force. So there will be definitely collision plus an electric field as well, a force due to the electric field because you have charged particles. So in the external electric field, so we have this m dv by dt will be equal to f collision plus f electric, so which will be of the form minus me v by tau and minus e2. So this is the force due to the electric field, and this is the collision. Now, uh, what we know that due to this collision force, that leads to an average velocity of 0 after every collision. But the average velocity will not be 0 if we have this additional electric field or a force due to electric field, because that will give a or that creates a force so such that the electron or charged particle moves or drifts. Okay, so this is why the name is drift velocity. So it drifts in a particular direction that is along the applied electric field. Okay, so so if let's say the electric field is a so simple case is we say electric field is it is a uniform or a constant electric field. So in that case, this rate of this acceleration dv by dt, so dv by dt is 0, and there is the force due to collision is equal to the force due to the electric field. So in that case, we will have an expression like, so the left hand side of this term will be 0, and the right hand side will be mev divided by tau minus e into e, and that implies I have some expression for this average velocity, which is given by minus e tau divided by mass of e. So now this average velocity or a drift velocity is given by or is proportional to the electric field, how much electric field I am applying. And now we can substitute it in the current density formula, which we wrote as Ne into V. And that gives me, so just substituting the value of the average velocity, I will get this J is equal to NE square tau by ME, which is equal to sigma into E. So this sigma, this conductivity that we defined, is given by NE square by tau into M. Okay, so this is a very simple model where a classical theory was used, kinetic theory of gases was used to kind of correlate this is sigma that you normally measure, right? The conductivity or resistivity that you can normally measure, which can be connected to some of the fundamental aspects of the charge particle motion. Okay, so the conductivity will be proportional to the number of electrons per unit volume, the charge, then mass, and of course a quantity, this tau, which of course it's not, you cannot really measure it, but it is related to the atomic or the motion of electrons in an atomic scale. So now how this equation will be modified if we are now applying a not a uniform field but an oscillating electric field. So let's apply oscillating electric field. So instead of a uniform electric field, so I have an oscillating electric field which is given by this kind of equation. So this is my amplitude, and this is the phase part of the of this oscillating electric field. And due to this oscillating electric field, so this average velocity will also have a oscillation of the same nature. So only the amplitude will be now related to what is the amplitude of this V, and this V, it can be a complex quantity. So this amplitude that we are writing, it can be a complex quantity. So not necessarily always it is a real. So now if you substitute this into this equation of motion, okay, so the equation of motion which we defined as me dv by dt is equal to minus e into e and minus me d by tau. So this is the equation of motion. So that remains the same. So we just substitute in place of v, average velocity, the oscillating velocity, and in place of e, so we substitute the oscillating electric field. And if you do a little bit of a manipulation or simple calculations, so what you will get eventually is your Jc will be equal to sigma. Now let me first, so me square tau by me into 1 minus I omega tau into E. Okay, so which is nothing but your sigma naught I omega tau EC, where sigma naught we are saying is NE square tau by M. So this is your DC conductivity. Okay, and now your sigma, which is your AC conductivity, is given by the DC conductivity divided by I omega tau. So this is the conductivity that will be modified due to this applied AC or a oscillating electric field. So in a conductor, so even a oscillating electric field will give rise to this oscillating conductivity. Now, now let's look at how this electric field will so let's say this is about a conductor. So because you have free charges, so these free charges produce or will oscillate with respect to this oscillating electric field. And due to this oscillating electric field, so you have a current density which is given by or there will be AC conductivity which varies as with omega. So there is a dependence on omega, which this dependence that is coming from the frequency of oscillation of the electric field. Okay, so now uh, let's look at a condition or a situation in case of dielectric. So in case of dielectric, you don't have these three charges, right? So in case of a dielectric, you have these bound charges which give rise to something known as your a dipole moment. Okay, so due to this electric field, so what you have is an induced dipole. So you induce an electric dipole within the atom, and this is given by this dipole is given by minus E into X, let's say, where X is basically the separation between your positive charge center, that is nucleus, and negative charge center due to the electron distribution. Uh, and when we think of if we are applying now AC electric field, okay, so before going into this AC electric field, so how this dipole moment is connected to your induced the electric field that has caused it. So this we can understand on assuming that, so let's make this picture so which will be then make it simpler. So I'm applying an electric field, so I have a separation of this positive and negative charges. Okay, so this is my P. Now I can assume this because this is a bound case, not a free charges. So this is a bound electron. So I can assume that this the force now acting between this positive and negative charges is similar to, or this binding is similar to a like a spring, or the, let's say, the negative charge that is attached to the positive charge through a spring. Okay, so I can assume it's something similar similar to a spring, and in that case the force, the restoring force that acts on the electron is equal to k into x. Okay, which is also equal to your, due to this electric field. So you have a force which is similar to a spring force or a restoring force equal to k into x, which is equal to, definitely this is the form of your force that is acting on the electron. So then we can write down, or we can find a relation between P and E, because we can write now x is equal to minus EE by K. So K is your force constant, or the spring constant, so to say. And P then will be equal to, so minus, so E square divided by K into E. So this is how your dipole moment will be related to your electric field with a proportionality constant E square by K. But we also know that the dipole moment is nothing but, if I have, sorry, so I know the polarization of such a dielectric is equal to the number of electrons into per unit volume multiplied by the dipole moment. Okay, so this is my polarization. So which I can write as N, so the substitute E square by K into. So this is my polarization. But polarization is also equal to epsilon naught chi E into E. So where chi E is the electric susceptibility. So now I can define what is my electric susceptibility. So epsilon naught chi E will be equal to N square by K, and that means my electric susceptibility is given by N square by epsilon naught K.
Sir, what exactly you mean by electric susceptibility?
Electric susceptibility is the response of your dielectric to electric field. So in a way we are defining, so what so this is so any susceptibility, when we define susceptibility in physics, so it is always related to what is the response of your material, or whatever we are talking about, susceptibility of that material with respect to some external perturbation or external influence. Okay, so here we are applying an electric field, then how this material behaves to that external electric field, so that the parameter which defines that, that is the susceptibility. Okay, and what the electric field basically does, it creates a polarization. So this is why we are writing a relation between polarization and electric field, which is defined by this susceptibility chi. Okay, so this epsilon naught is again a constant which comes due to keep your dimensions the same on the left hand side and right hand side. Okay, so otherwise chi itself does not have any unit. Okay, so it is a dimensionless quantity, so it's just a parameter which tells you what is the response of a material due to external perturbation. So similarly, you also have a chi magnetic, that is a magnetic susceptibility. So we briefly discussed about that. The magnetic susceptibility also will be proportional to your, this is a relation, or you can define as magnetization divided by H. Okay, so this is, that means how a material responds to an external magnetic field H. So what is the response? Basically the response is there will be a dipole, magnetic dipole moment, or that results into magnetization. Like in case of dielectric you have a polarization, so here you have a magnetization. So this is what the susceptibility means. Okay, so this is the susceptibility of a dielectric material in presence of electric field. So now we are applying a electric field which is also varies as a function of time, exponential I omega t. Now so what will be this motion of the electron which is bound in the atom? So these electrons, remember, these electrons are bound to the atom, so they are not free electrons, so they cannot move anywhere, like in case of metal. So how they will behave to this electric field, oscillating electric field? So let's first write down the equation of motion for the electron. So I am writing this left hand side is basically tells you that the mass of the electron d square x by dt square, that is x is the displacement of the electron, and so I'm writing the acceleration. So the force that is acting on the electron is equal to minus k into x. So this comes from the assumption that we are assuming it is like a spring. So the electron, it is bound to the nucleus and it moves like a spring. So therefore it can move up to a certain distance x, and there is a restoring force that acts on the spring, that is minus kx. But not only that, also what you have is this so there will be some other kind of forces that also acts on the spring, because it is not. So if I write equation just like this, it will be, so you can say the electron will just make a simple harmonic motion. Okay, so if you go back to your remember your classical mechanics, so this equation represents a simple harmonic motion. Okay, so this is me d square x by dt square, which is equal to just minus kx. It is a simple harmonic motion, but electron is not doing that. So of course the first thing is it is similar to a spring, so there is a restoring force, but there is also a damping which stops the electron just doing this simple harmonic motion, and normally this damping force is proportional to the velocity of the electron. So this is dx by dt. And then of course you have a external force due to the electric field that is given by this. Okay, so this is the external force due to the electric field. So this is your damping force. Okay, so these are the forces which acts on the electron, and you can write down the equation. So the on the left hand side, what is the force acting on the electron, will have these three components. So I can write down now this differential equation. So d square x by dt square. So I can write it as so let's take, so gamma by me dx by dt, then plus k by me x is equal to minus e by me t0 exponential I omega t. So I'm just rearranging this equation. So you can write this equation also like this, defining some of the parameters which you already familiar with. Okay, so this big gamma is equal to small gamma by me. That is your normally you call as a damping parameter, and omega 0 is your frequency of this simple harmonic motion, so which is nothing but your square root of k by me. And this kind of equation also, in classical mechanics, so this resembles something known as a force damped harmonic oscillator. So the electron motion is resembles something similar to a force damped harmonic oscillator in a dielectric, in presence of an oscillating electric field. So now you can, so the solution So a trial solution here, you start with x equal to x0 exponential I minus I omega t. You substitute that, try to solve it, and what you will eventually then write down an expression for the susceptibility. So you can write, so by substituting that, so you will find the expression for P, okay, into E epsilon naught into something, and that something part is your electric susceptibility, which is given by NE square divided by epsilon naught ME into minus omega square minus I gamma omega plus omega. So this is the electric susceptibility of a dielectric in presence of an external electric field. So which depends on the frequency of, so this omega 0 is the natural frequency of oscillation. That means if there is no force, no damping, so if it moves as simple harmonic oscillator, so this will be the frequency with which the electron should oscillate. But in presence of a forced electric field with a frequency omega, so the susceptibility is now modified, which is written something like this. Which also you can see that when if omega equal to 0, so the expression that we got earlier for chi e, we will get that expression chi this. Okay, so when omega is equal to 0. And also you be careful that here we have an imaginary term as well. So this I here represents an imaginary term. Okay. So you can also write it in a how do you say? You can write like the real part and the imaginary part of the susceptibility and so on. Okay, so also in the book you will see something related to another kind of matter, another kind of state where electric field is very important, that is plasma. So plasma is a state of matter which has electrons, ions, also neutral atoms and so on. So it is a mixture of all these different charged particles and neutral particles. And these plasma responds to a external electric field in a very different way, and that is also like another big field of physics where you can create plasma and then try to confine plasma applying like electric field and magnetic field and so on. So the plasma also behaves differently in presence of this electromagnetic field or external electric field. Okay, so this is about some of the parameters, material parameters, how this gets affected in presence of electric field in conductor and dielectric. So similarly, you will also have another important aspect of this electromagnetic field is whether this like what we saw in the morning session, that if you have a dielectric, so which where the electromagnetic field or the Maxwell's equation get modified, and you can write down a wave equation similar to the wave equation for free space, but now the wave propagates at a slower speed due to the permittivity and permeability of the material, which gives rise to basically is related to your refractive index. Then Similar, so what will be the propagation in a conductor? So in case of a conductor, again, so you will write down all the equations, Maxwell's equation. But what interesting thing happens in a conductor? So since you have a lot of free charges, so you don't have any accumulation of charges on the conductor, even if you are applying a oscillating electric field. So immediately, so even if a charge builds up, so it will be for a very short time, and immediately it will make sure, because we know that within a conductor electric field has to be 0. Then how the wave equation looks like for a conductor? So this is interesting because when you look at the expression of, so let me write down the fourth equation, Maxwell's equation in conductor, which is given by this term. Okay. And now if I take the curl of this vector, okay, so I will get an expression that is, okay, sorry, so I have, yeah, so this is the fourth equation and this is the third equation, which is minus del B by del T. So if I take, let's say, curl of this equation, so del by del T into curl of B, and this is nothing but your del, so the first one will be del into del dot E minus del square E, so will be equal to del by del T, and in place of curl of B, so if I substitute that, so I will have this expression plus again, so minus term would be there, minus mu epsilon del square E by del T square. And for a conductor, so we can say a del dot E will be 0, because rho OF will be always 0. Or even if there is a charge buildup, it will happen for a very short period of time. So instantaneously, this rho F, any free charge, so they will rearrange in such a way that there will be no existence of any charge accumulation, so to say. So rho F will be always 0. So del dot E will be 0. And therefore, your del square E will be equal to mu into sigma del E by del T plus mu epsilon del square E by del T square. So you'll also have a similar expression in case of B. So the wave equation is not like what we have seen it earlier. So we have an inhomogeneous equation because we have this term, okay. So this makes the equation inhomogeneous, and you will not find a simple solution for E, but you can start with a trial solution, which is of this nature. So this is, let's say, a trial solution. And if you substitute that, so you will find a condition, okay, a relation between your Kc, which is your web vector, which will be equal to I omega mu sigma plus mu epsilon naught omega square. So that means your web vector becomes complex. Okay, so you can write it in a simpler form using different notations, so that you can see in the book. But what I want to say here is your wave vector itself becomes complex, Okay, so when we talk about an electromagnetic wave, okay, so the in uh, in the conductor it becomes complex, so which results or which means that uh, there is a certain depth up to which the electric field can penetrate. Okay, so if I take a conductor, so the electric field can penetrate up to a depth, a delta, okay, so which is known as the skin depth. Okay, so this is a known as a skin depth. So up to this, up to a certain value delta, so which is of course in terms of a distance. Okay, so the conductor in presence of electric field or a oscillating electric field, so there will be some penetration of the electric field into the conductor up to a depth delta, uh, which of course depends on uh, so there is so it depends on, of course, the frequency and yeah, so the skin depth will be related. So you can write as 1 by delta is equal to omega into mu epsilon divided by 2 into 1 plus sigma by epsilon omega square minus 1 to the power half. Okay, so this is the skin depth that will be equal to so 1 by delta. So it depends on the frequency, depends on your permittivity, permeability, and also it depends on the conductivity of the material. So this there should be another half square root here. This is how the expression looks like. Okay, so you can calculate if you know the material, what is the permittivity, permeability, and the conductivity of the material, and if you know what is the frequency of the incident electromagnetic radiation, so you can calculate up to what depth the electric field can penetrate into this material. Okay, so another thing which also is interesting when we talk about this electromagnetic field. So there is something known as so this electromagnetic wave, or when we talk about a wave, so you have, let's say, something known as a phase velocity and a group velocity. So let me just tell you what is the difference between this. So when we talk about this electromagnetic wave or a classical wave, so let's say I have an electric field. Okay, so this is, I am defining as it has an amplitude E naught, and then this is the phase. So in most of the electromagnetic theory, so what we will see now forward, so it is always we are writing it in terms of these some complex form. Okay, so exponential is like I exponential I some factor, phase factor term. Okay, why? Because this helps us in solving these equations quite easily without really missing out on the physical interpretation. If you want to see any physical interpretation of this, so you always have to take the real part of this electric field or magnetic field. But if you write it in this complex form, So then, because you have always this derivative terms, okay? So whether it is a time derivative or a space derivative, so it is always easy to perform this derivative on exponential term. So that's why we are writing it always in electromagnetic theory. You will see it is always written in this form, okay? But this is for a mathematical convenience. Although if you want to extract a physical meaning, so you can take the what is the real part of that uh, expression and then interpret the physical meaning of that. So we are writing the electric field. This is what defines a like an electromagnetic wave which propagates along a x direction. So this is propagating along x direction with angular frequency omega. So of course, this is also a monochromatic wave because I have only one frequency omega. Now the phase velocity. So the phase velocity is defined here as v phi, which is a constant velocity of the phase. So what is the phase part of this wave? So always, whenever we define a wave, always we define with the amplitude and a phase. So what is the phase part of the wave here? So the phase part is kx minus omega t. This is the phase. Now, if it moves at a constant speed, the constant speed means if I take a derivative k dx and omega minus omega d tau dt will be always equal to 0. So this is a constant phase velocity. So this implies your, so here we define the phase velocity dx by dt, which is equal to omega by k. So this is known as your phase velocity of the wave. So which means, so the phase velocity is same, which means the amplitude of the wave is same everywhere. Okay, so this is the one, it is a monochromatic wave. The amplitude is same everywhere. And the phase, like it moves at a constant velocity. Okay, so a representation of this I can show you. So let's say a physical wave which moves something like this. Okay, so it has exactly the same amplitude everywhere. Of course, so now you can define what is the frequency, what is lambda, what is omega, and what is k. So what is omega and k basically of this wave? So k wave vector we normally will divide by 2 pi by lambda. That is your wave vector. So I hope you are familiar with these notations. Okay, so omega will be equal to 2 pi into f. So f is your frequency. Lambda is your wavelength. Okay, so these are the terms which are used, or parameters which are used to define your wave. So get familiar with these terms. So this is a wave, a monochromatic wave with a constant phase velocity. Now, what is a group velocity? So group velocity means I need to have a group of waves, of course. And why do I need a group of waves? So normally, when we say you want to carry any information, so for example, in communication using optical fibers, okay, so where we are moving a data from one point to another point, okay, so like the internet, you might have heard like you have this geo fibers, or this optical fibers which are connected, to which you connect to the internet. So there, when we talk of propagation of any information or any data, so that cannot be done with one single wave. So there you take a different waves superimposed on each other, which form a group of wave. And due to this superposition, so what you get is a wave with a variable amplitude. So the representation for a group wave would be, let's say I have a wave with this frequency, then, so these are different traveling waves. Okay. I have, so there can be many such waves which superimpose, and what you get is a wave packet something like this. Okay. And this wave packet, so when you look at the amplitude part of this wave packet, so this is, let me draw it in another color. So the amplitude part, so when you look at this amplitude of this group of waves, so it is something like this. So now this wave packet so travels and carries the information. Okay, so this is how in a optical fiber, for example, a wave packet moves and carries the information. Now this, the velocity at which this peak, so you are looking at this peak position, so how this envelope, so this is also known as an envelope wave. So how or what is the velocity of this wave packet? So this is known as the group velocity. Okay, so the group velocity here is your the velocity of the envelope wave. So this is which you get due to a superposition, so not superimpose. Okay, so this is a superposition of these individual waves which have a slight variation in their wavelength. So the wavelength may not vary too large. So there will be a small variation in lambda. So for some it will be lambda, for some it will be lambda plus delta lambda. So delta lambda 1 or delta lambda 2. So some variation will be there. And when the superposition due to that, or interference you can say, so you will get a wave packet, and that wave packet basically carries the information. And the velocity of that wave packet is your group velocity, and which is normally defined as d omega by dk. So here this omega, d omega by dk, so omega is a function of your wave vector k. Okay, so but if I take just a monochromatic wave, a simple like what I have described here, so here omega is just, it is constant, so it does not depend on k at all. Okay, but in this case omega is a function of k, and this is which results in a wave packet which basically carries your information. So this distinction you need to know when we talk about so this kind of situation also arises in mechanical wave, in optics, okay, in electromagnetic wave, also in quantum mechanics. Also you also encounter about this wave packet, phase velocity, and group velocity. Okay, the next thing which is interesting. So based on, so when we look at electromagnetic wave, Okay, so we know so once we have established what is the basic foundation, the principles, the Maxwell's equation, which describe the electromagnetic wave. Now, whatever basically afterwards was done is about its applications. Okay, so a very nice thing about electromagnetic theory is people had done a lot of experiments in optics, but there was no complete theory to explain all those experimental observations. So in optics, there is a reflection, there is refraction, there is dispersion, there is transmission. So those really could not be explained using any theory until the arrival of this electromagnetic theory. So once electromagnetic theory was established, one could use it and give a very nice theoretical understanding of optics. So this is what we will look at briefly. And this is a lot of, so therefore electromagnetic wave has a lot of applications in optics. So you can describe all optical phenomena using just simply solving Maxwell's equation. Before looking at or to find an expression for reflection or refraction or transmission, okay, so what is important to know that if I have a, let's say, interface which basically divides my region 1 and region 2. So this is, let's say, this is a dielectric 1. This is one medium. This is another medium. So it has its own permittivity and permeability. So this also has its permittivity and permeability. So now how the wave propagates at the interface. Okay, so I have an electric field and a magnetic field. So similarly, if I am talking about a dielectric, so I will have a electric displacement vector and H field. So how they propagate at the interface when they go from one medium to another. So this is all governed by something known as a boundary condition. Okay, so this is basically the most basic idea or thing which will determine or can be used to find out the electromagnetic propagation from one medium to another medium, and consequently you can talk of reflection, refraction, and so. So when we talk about the boundary condition of how the propagation will occur from one medium to another, so basically what you do is you divide the electric and any of these vectors, so you divide into two components. So you will either write, so E you write is E perpendicular and plus E parallel. So similarly, B also you write as a B perpendicular and B parallel. What is the perpendicular and parallel component means? So the perpendicular component here will be this perpendicular to this unit vector n cap or along the n cap direction, which is perpendicular to the plane that we are talking about. And the parallel component will be along this plane. So this is the interface which separates your medium 1 and medium 2, and now you can write the component of electric field and magnetic field parallel to this plane or perpendicular to this plane. So you have to write all these vectors in that and see which one is continuous and which one is discontinuous. So so here you just simply just use this different, like the Maxwell's equation, and see the continuity. So this can be easily done once you go through this section in the book. So I'll just write down those conditions. So if I write, so this is we are looking at the perpendicular component in medium 2, and this is also the perpendicular component medium 1. So this is epsilon 2, the perpendicular component of electric field, minus the permittivity in medium 1 and the perpendicular component of electric field, that will be equal to 0. The B field perpendicular to this interface will be continuous. So that means B2 minus B1 will be equal to 0. So this magnetic field is continuous. And the electric field that is parallel to these two mediums or to the interface, this will be continuous because E2, the parallel component, this is equal to 0. So the parallel component will be continuous. Electric field, the parallel component of electric field is continuous. The perpendicular component of magnetic field is continuous. Now, the parallel, so these are all vectors, although we are writing in terms of their components, we are saying it is component, but these are all vector terms. And the magnetic field is discontinuous, but the H field, so because Bu2 by mu2 will be equal to H2, the magnetic induction, so that is continuous. So these are the boundary conditions, and based on that, you can write down how much of the electromagnetic wave will be. So if I have such a interface, okay, so which separates my medium 1 and medium 2, dielectric medium 1 and dielectric medium 2, so I can write down how much electric field will get reflected, how much will get transmitted, and so on. So this exercise also you can do it. Just I will briefly just discuss that. You can elaborately look at it. So I am writing, this is the incident electric field. Okay, so this is let's say it is traveling along, this wave is traveling along the Z direction, okay, and the electric field is along the X direction, okay. So remember, we are talking about a transverse wave, okay. So the electric field is along X axis, the amplitude, so it is oscillating along the X axis with this page, but it is propagating along the Z direction. So that is why this phase term has K1Z. So similarly, the BI, the magnetic field, will be along the Y-axis. Okay, so the amplitude will be along Y-axis. So Y cap direction. And in fact, also for such a, so this kind of wave is also known as a plane polarized wave. So what we are describing here is a plane polarized wave. So polarization, so plane polarization means So the electric field here is polarized along the x axis. So if you define your x and y and z, so this is, let's say, z direction, this is propagation. So the electric field is along x and the magnetic field oscillates along the y direction. And this is a plane polarized wave. Okay. And what is the velocity of the wave here? So this velocity of the wave is just the phase velocity that we are talking about. So omega by k1. This is the phase velocity, which will be equal to, so if you are in medium 1, so it will be equal to the permittivity of this medium, so epsilon 1 by mu1 into epsilon 1. We can also find a expression or relation between this B and E. Okay, so using Maxwell's equation, so what you can do is, so just try to calculate what is curl of E is equal to minus del B by del T. Okay, so just substitute what we have written here, E and B. So just write that down. So you will find a interesting relation between B and E, which is given by a cross product of the wave vector k into E divided by omega, which if you now simplify a little bit, so you have so k, this is the propagation vector, so this is z cap, and E is along x cap, so that's why the B field will be along the y cap direction. And if I just write down in terms of the unit vector for k, so I can write this as omega by k. So this is equal to E divided by V. So this is your V1. So if it is in the k1 direction, so let's say we are saying this is k1. And therefore, the amplitude, so if you now look at the amplitude of this B, so B, when we wrote this amplitude, so B0I, so will be simply equal to E0I divided by V1. Okay, so this will be the just the amplitude or the magnitude of the magnetic field. So what you see, I observed something interesting here. So typically the magnetic field, so the V is, let's say, if it is a free space. Okay, so for free space, you can say this V1 will be equal to C. So in that case, your V0I will be equal to E0I divided by C. So you can see the amplitude of your magnetic field is much smaller because C is quite huge. So for any given electric field, so the amplitude of the magnetic field always is very small. Okay, so this is a interesting observation, which normally you will not find in books, but this is why, for like most of the times, your magnetic field. So when we talk electromagnetic wave, the propagation of electromagnetic wave, so we typically only discuss the propagation of electric field alone. So mostly you can discuss both electric and magnetic field, but it is normally what happens, if you know how the electric field propagates, so you know and you know what is the direction of propagation, you know the magnetic field is actually very small, the amplitude is small. Also, it will be always perpendicular to both electric field and the propagation direction. So in most of the optics experiment actually, or in theory, so people only treat how the electric field that propagates, and that is good enough. You don't need to really think about magnetic field. But here you can, in the beginning, you can do that. In the book, it is given because you will then appreciate how the boundary conditions that we have written, how that looks like when we talk of an interface and different media. Okay, so using this, starting with these incident electric field and a magnetic field, we want to see what is whether we can explain the reflection and transmission through a medium at an interface. Okay, so you can write down, so if I take, let's say, so let me define the medium here. So this is my z direction, okay, and this is where I define x, and this is my y direction. Okay, so the electric field I am saying is like this, and they are propagating along this direction. This is my magnetic field. Okay, this is, you can write it as a subscript 1, or you can say this is an incident. Then clearly there will be a reflection of this. Okay, so there will be reflected electric field ER, and which propagates along the minus z direction because it is a reflection. Okay, and then there will be also a transmitted electric field which propagates at a speed v2 because it has entered into the second medium. So this is medium 1, this is medium 2, which has permittivity, permeability mu1 and permittivity epsilon1. Here you have mu2 and epsilon2. So since the velocity will be different in two different media, so this is how the transmitted wave would look like, and Pt also will be like this. But the reflected one, the magnetic field, will be along minus y direction. Okay, so this is because we have reversed the velocity, and we know that this B is it's a dot or a cross product of K cross E, right? So now since I have reversed the direction of K, so that means B will be also, the direction will be reversed in the reflected case. So these are all, we are using simple, the equations might look a bit complicated, but we are just using these equations using vector identities and vector equations just to find out how the reflection, refraction, the transmission will happen. Yes.
Today, whatever you taught regarding the kinetic theory of these electrons, that velocity and drift velocity, that is there in Griffith, sir, any other book?
That is, yes, partly in Griffith, yes.
Any other author, good author?
I mean, if you look at any solid state physics book, you will find
Okay,
that.
fine.
So any solid state book you take, so this will be explained there also.
Fine.
Okay, so you can write down this exclusively the expression for the electric reflected one. So let's say I'm writing this ER. So ER vector will have the amplitude E0R exponential minus K1Z minus omega t into x cap. Okay, so this minus sign here is because I am talking about propagation which is opposite to the z direction. This is the reflected wave. So similarly, BR will have E0R divided by the minus E01 by V1 into exponential I minus K1Z minus omega t into y cap. Okay, so this minus sign ensures that the B vector is along the minus y direction. So similarly, you can write the transmitted wave as E0t exponential I k2z minus omega t x cap, and the corresponding magnetic field as I k2z minus omega t and y cap. So what you can see here, only the amplitude will be different. So let me just write down as E0 divided by V2. So what you can see is, when we talk of reflected wave, so the phase factor remains the same in each case. Okay, so this phase factor is exactly the same. So the amplitude, they are different. So similarly, in a transmitted wave, also the phase remains same. The amplitude changes, and the polarization state remains intact. So that means if electric field or a magnetic field is along x cap, so it will remain along the x direction or y direction. And just to complete, so V1 is equal to mu1 epsilon 1, and your V2 is equal to 1 by mu2 epsilon 2. So this is your respective velocities in medium 1 and medium 2. So you can in fact find out, but we don't know what is the expression for this amplitudes will be. So now you can use the Maxwell's equation, okay, and find out what will be the form of E0R and E0T. So you have to use so you have to write it in terms of their so in an example, so you will see how it is done in the example. So quite what they have done is, so you assume, so let's say here I have written it down, everything how it should look like, but actually we don't know whether after reflection, okay, so electric field, so you can take the case of only the electric field, so without talking about the magnetic field. So what you can do is, you can say, okay, so I am saying the electric field here should be remain the same along x cap. So that means it does not have any y component, okay. But you can start assuming that it has a x component. So that means this vector, ER vector, has a x cap. So the x component will be defined by x cap, and also it has a y component. And then when you look at the continuity equation at this interface z, so which is defined as z equal to 0. So at this point, so if you apply the continuity equation, so you will see that the y component will vanish for electric field. So similarly, the x component of the magnetic field will vanish, and that will give it will ensure that what we have written is the correct form. Okay, so this is everything like what we derive in optics from this point onward will be basically you just write down the wave equation, this electromagnetic wave, the incident wave, reflected wave, or transmitted wave, apply the boundary condition, and you can derive almost all optical, like the equations or formulas that you can actually calculate from that. So this is all like you do a little bit of mathematics and doing a bit of calculating writing the exact component form, and you can calculate it. So what you will see is you can find out what is the refractive index, what is the reflection coefficient, what is the transmission coefficient. Okay, all these you can have an expression in terms of the amplitude of electric and magnetic field, and which you can also write it in terms of the corresponding refractive indices and so on. So this also you can extend. So here what we are talking about, the simple case where the incident is normal to the plane, you can also apply this when the incident is at a certain angle, and in that case, if the incident is at certain angle, so in optics, it will follow the Snell's law. Okay, so this also you can derive using the oblique incident. So you have a normal incidence, then there is a oblique incidence. The oblique incidence where your electromagnetic wave is incident at a certain angle theta to the perpendicular. So in that case, you can also get the Snell's law. Okay, so there are several other optical phenomenon which also you can describe. For example, the total internal reflection, dispersion, and so on. So you just go through the text, and if you follow the examples that are described, so you can easily understand how this is done. Okay, so this is all about, you have to write the wave properly, okay, with, like we are writing it with the amplitude, with the phase correctly, with what is the component form, so whether it is along x or y, and always you have to remember that your wave, the amplitudes or the electric field and magnetic field, they should be always perpendicular to the propagation direction, which is the, so normally in most of the cases it is taken as the z direction. So you have to be careful about that. So any question so far?
Sir, any specific author for the solid state physics?
Solid state physics, I think it I mean, there are foreign author books, but you can also follow, like, I mean, Kittel, Charles Kittel, for example, or you can say, so Indian author is, there is, I think, Babbar and Puri. Okay, so there is an Indian author book which many universities follow. There also you will find this. Okay. Yeah. Any question?
Thank you, sir.
Okay, so another interesting aspect of this electromagnetic theory or electrodynamics specifically is related to like we discussed about the scalar and vector potential, right? So if you remember, so we talked how you can write the wave equations in terms using scalar or not the wave equation. So the Maxwell's equation using the scalar and vector potential, and eventually using Lorentz gauge, you can write the wave equation for scalar and vector potential as well. So now this will be used to calculate something which goes into a more advanced form of electrodynamics. Okay, so which talks about how you can get a radiation or a radiation field at a distance. Okay, so you can imagine, so let's say, and this electromagnetic radiation can travel really far, right? So when you have, let's say, radio communications, for example, okay, so this radio communication can happen over 1,000 kilometers. Okay, so this radiation travels 1,000 kilometers, and you can still capture it, and then you can tune into, okay, of course it is tuned to a certain frequency, but that frequency does not get attenuated, so it travels 1,000 kilometers, and then you can receive it using a receiver, and you can listen to any song or any news or anything on your radio, for example, which was like the first application of this, the telecommunication that was happening in earlier. Yeah. So now everything is, of course, we are talking about 4G, 5G, and then eventually to 6G probably. So, where the communication now we are talking in terms of in a microwave frequency range, but still they where this radiation travels from Earth to a satellite. Okay, so communication satellite, and then it is basically telecast or transferred to different regions where we receive and then get connected. So this is also still happening through this propagation of electromagnetic radiation, and this radiation travels really far away. So how this happens? Because when you look at okay, so if you think in terms of a material, okay, right? So you have charged particles, you apply electric field or something, and you can produce an electromagnetic field, but those electromagnetic fields don't really travel too far. So why some of the electric field or magnetic field they travel so far and some does not? So these are the some of the questions which can be addressed. So how, let's say, these radio waves travel so far? In order to understand that, so what we need to first look at how this radiation actually, or one can understand how this radiation field propagates. Now, the question, of course, they're all like you write in terms of electromagnetic wave equation or using Maxwell's equation. But when we think of this electromagnetic radiation or a radiation field, so you say, okay, they are propagated in a free space. There is nowhere in a free space, there is no charge, no electric current, but still they are able to propagate. That is good. But there must be some source somewhere which should generate this electromagnetic field. Okay, so without any source, so you cannot have an electromagnetic field in the first case. Only if you produce the electromagnetic field, so it may propagate without need of any medium. So it can move in free space, in vacuum, anywhere it can move. It can self-sustain itself. But at least when it is produced, it has to be due to some charges or due to some electric current. Now the charges, when we talk of a changing electric and magnetic field, so it means the source also changes. Okay, so when we talk a magnetic field which varies as a function of time, so that means the source also has to vary with that particular time period or with that frequency, and that will generate that particular radiation. Okay, so if I say just to like okay, so if I say you are getting a sunlight, right? A sunlight, let's say visible light, we are saying. So visible light, it's a blue or let's say red or yellow. So it is comprising of this, let's say basic 7 colors, so which comes from sunlight. So that means how this is produced? This is produced due to some atomic or electron excitation, right, within the sun. So there is some this atomic transition that is happening, and due to those transition, so then there is a source that creates this electromagnetic wave. Now that electromagnetic wave basically propagates and reaches us. So always there must be some source of this electromagnetic radiation. Now if this there is a source, now what happens to this electromagnetic radiation when the source itself is oscillating? or it is varying as a function of time. So this is the most like one of the advanced form of electrodynamics, where you want to understand if my source, the current distribution or charge distribution itself, has a time dependence. Okay, so how that is going to affect my electric field and magnetic field. So what we have seen in electrostatic and magnetostatic is we have a static uh, stationary charge distribution, and they follow Coulomb's law. So similarly, we have steady state current that gives rise to the Biot-Savart law or Ampere's law. But now if the charges itself move, or this steady state current is itself, it is changing as a function of time. So whether those laws are still satisfied or not, whether Coulomb's law is valid, whether Biot-Savart law is valid, actually it is not. So they will be modified if these charges or the steady state current are not anymore steady or stationary. So this is again the part of a one part of electrodynamics. Okay. So which is your radiation and electrodynamics. Okay, so this is, in a true sense, you can say you are going into a well advanced form of electrodynamics. So we'll start with something which we already discussed. Now, in order to find a relation between this charge distribution, time variation of charge distribution, so we have this rho and J, which we say has a time dependence. Okay, now how this is going to affect your electric field, magnetic field, this is what we are interested in. Now you can say, okay, we have the Maxwell's equation, right, which we wrote for electric field and magnetic field, which contains the charge distribution and the current density, and we just introduce the time dependence and we will find a relation between E and B, but that is not that straightforward. And that is why we have to take the help of the scalar and vector potentials, and we can actually use the write down the Maxwell's equation in terms of this charge, the scalar and vector potential, and use this time variation of rho and J to calculate how the scalar potential and vector potential are going to get affected, and from that we can then calculate the electric and magnetic field. So that path or that process is a relatively simpler compared to directly computing so E and B from rho and J. So what we will, instead of take a path where we first calculate what is A, so which has a function of position and time, then a phi, which is also a function of position and time. So first you calculate using rho and J. So you calculate this, and from this you calculate E and B. So this is a much simpler way to do that, and this is done using a formalism which is known as a Green's function formalism. So what is this Green's function formalism? So we will discuss that and see how this is applicable to our case. So this Green's function formalism is, again, it is a mathematical tool that we are going to use to in our electrodynamics. Okay, so this is developed purely by mathematicians. Okay, so only we physicists, we are using these Green's function as a tool to calculate our or solve our differential equation. Okay, so a very general differential equation, which is a inhomogeneous. So if I have inhomogeneous differential equation of this form, okay, so I am just writing down which will be familiar also to us when we write the scalar and vector potential terms. Okay, so this is a inhomogeneous differential equation, which where you want to find out what is the solution here. The solution means what is u r t. So how do we find a solution? So in the formalism, what they have done, okay, so here this f is basically is a function of position and time, and the trick here is so, and to put it in a context which will be familiar to us. So what we are interested in, we have some function here, rt. Okay, this is our source point, so to say. So this FRT in our case will be our charge distribution or our current density distribution. So this is our source point, and we want to find out, so instead of this, so we want to, sorry. Okay, yeah. So we want to find out what is this is our point of interest, so to say. This is where we want to calculate what is the field, electric field at this point P. So if we change this F here, so how this is going to affect the function U. So we want to find out this U R T here. So how this is going to get affected. Now the question is, if there is any change in F, so how quickly or how slowly? So of course there is, so this is, let's say you say as vector r, this is r prime, so r minus r prime. So this is the position vector of your point P with respect to the source point, and at the field of interest or field point, so if I do any change in F as a function of time, so now the question is how fast or slow this information will reach at what time. So then that will be reflected. So in the field point. So that means if I say, if I want to calculate the field U at this point at a particular time t, let's say, so this will be actually governed or decided by what is the value of f at an earlier time t prime, okay, not exactly at t. So it will be what is the configuration, charge configuration at earlier time t prime, because this information needs to travel from this point, from your source point to the field point. It needs certain time, because if it is instantaneous, if I say I have changed the source, the charge distribution at the source, and the electric field will change instantaneously. That is never going to happen because that is going to violate your condition that information can travel faster than light. So minimum time, how much time it requires at least. So at least it can travel at a speed c. Okay. So now the time required for this information that something has changed here to reach this field point will take how much time it will take. So time that will be taken will be
R dash by C.
R dash by C. So or R is R by C. So this much time is required so that this information from any changes has happened at this source point will reach the field point. So that means if I want to find out what is the actual field value at point P at time t depends on what is the charge distribution at the source point at an earlier time t, let's say t prime, which is given by your t minus r divided by whatever the velocity that we are writing here, vp, or if it is traveling at a speed c, so it will be what is the function of r t prime, so which is how the function looks like at earlier time t minus r divided by vp. So that will decide what is the field the function will be at time t. So this is very important. So this concept you have to understand, and then the rest of the things will be again doing a lot of tricky mathematics. So once
this one is from which unit, sir?
so this is, we are talking about the unit it is unit 9. Okay,
Thank you, sir.
so this is unit 9. So basically whatever in this unit 9, 10 and 11, I think there are 3 units here, so all are related to this concept only. So so here, so this is where we take a help of Green's function formalism, because the formalism tells us we can calculate or find a solution for u in this kind of situation. So we can, the solution will be minus 1 by 4 pi 1 by r minus r prime modulus. So f of r prime t minus r prime divided by r by vp into dv prime. So what the solution tells you that the function u at a field point where you want to calculate what is the value of this function rt. So this value of function, what we are interested is basically we are talking of potentials. Okay, so not electric field, magnetic field, but potential. So what will be the potential at this point is given by the integral. So 1 by r minus r prime. So it is inversely proportional to r minus r prime. And then the function at r prime and at a time t minus r prime minus r divided by vp. This is also this time also known as t so this is, sorry, so this will be r, so we have to write it properly, r minus r prime. So this is r minus r prime, the modulus, divided by the velocity with which this information moves. So this is known as a retarded time. Okay, so the function depends on what is the value of this f at a retarded time, and you take a derivative, integral over this volume dv prime. Okay, so small volume, so you take a small volume, and then you just integrate over this entire volume, where you have distributed your charges or your sources, so to say. Okay, so is it clear? So this is where we will use the Green's function formalism. So we are not deriving how you obtain this solution. So this is also, if you are interested, you can look it up if you are really into mathematics. But in physics, we just use this concept and take the help to find out the solution. So now what we will do is we will write down the corresponding wave equation, the Maxwell's equation for scalar potential phi and vector potential A, which is given by this, which we did earlier in the morning. So del square A minus 1 by c square del square A by del t square equal to minus mu naught j. So we are using here the Lorentz gauge condition. This is why we could write these two decoupled equations. So we have decoupled phi and A. So equation 1 has only phi terms, equation 2 has only the vector potential term. And this condition is del dot A plus 1 by c square del phi by del t is equal to 0. So we are using this Lorentz gauge condition, and now we can simply, so we have written down this. I am not writing any r and t dependence, but now we will introduce the function as a function of r and t, and then use the Green's function formalism to write a solution for this phi and A, where we are interested to calculate what is the potential, scalar and vector potential, and then we can, from that we can then calculate what is B, E and B, and we will see. So there is a bit modification to the Coulomb's law as well as Biot-Savart law, which is understandable, but this leads to a certain kind of a radiation field, which basically what we observe when we think of electromagnetic radiation from sun, or a electromagnetic radiation that travels via radio wave or microwave. Okay, so all these are a consequence of that. Okay, so any question? So we will stop here for today. So tomorrow morning we'll try to find out these different types of radiation. There is electric dipole, there is magnetic dipole radiation, and then we will delve into a bit of special theory of relativity. Okay, fine. Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.